Hello, I'm going to present our paper on building interpretable models of black box agents. Here is a black box agent whose internal structure is assumed to be unknown, but whose behaviour we want to model and ultimately understand. In a Markov decision process, this agent lives in an environment whose state it observes before producing an action, which influences the state for the next time step. When we talk about modelling the agent, we mean producing a parallel system that looks at the environmental state and predicts the agent's action as closely as possible. By using any loss to update the model parameters, we have vanilla imitation learning. Our aim here is interpretability, so impose a structure on the model, which means we can understand it and gain some insight into the agent's behaviour. We decompose the model into two stages. The feature generator phi observes the state and outputs a vector of individually interpretable features. These are then fed to a rule-based policy function, pi, whose structure is also easy to interpret and analyse. Here's the learning objective for our model. We want to minimise the error in action prediction, subject to this decomposition into feature generator phi and rule-based policy pi. The hypothesis is that building an understandable model that mimics the agent's behaviour provides partial understanding of how it may operate under the hood. We generate interpretable features by recursively applying a set of elementary operators to the environmental state. Our interpretable policy is learnt from the class of binary axis-aligned decision trees over the generated features. We deploy our model in a traffic simulator, in which multiple vehicles use a common policy to navigate a road while avoiding collisions. Our experiments use two hand-coded policies. The first is itself a small decision tree. In theory, this can be modelled perfectly, since the space of interpretable models does include the true policy. This isn't the case with the second policy, a set of continuous control laws which can only be replicated partially by a tree of finite depth. The internal structure of the policies is entirely hidden from the model inference process. Our aim is to recover this from observational data. I'll now discuss the feature generator. Using domain knowledge, we define 8 elementary operators, which do things like query the location or speed of a vehicle, or find the nearest vehicle or junction in front or behind. Using these building blocks for any given vehicle, we can generate a host of meaningful features, like this one, which is the distance to the nearest junction, or this, which is the relative speed to the vehicle in front. In total, 308 features are possible. The first target policy uses just 6 of these, so we face a challenging problem of feature selection. Our learning process has 5 stages. For each target policy, we start by collecting a dataset of environmental states and vehicle actions. Treating all vehicles separately, we use the feature generator to create a vector of all 308 features, producing a large dataset to use for learning. We feed this to the CART algorithm, which grows out a decision tree to predict vehicle actions given the 308 features. To prevent overfitting, we then use pruning to gradually cut the tree back down again while preserving accuracy. We pick several trees to evaluate, which give a nice balance of complexity and accuracy on a validation set. In short, level 0 is the completely unpruned tree, and level 5 is the smallest, heavily pruned tree. Here are predictive accuracy results on a test set. Each column is for one of the 5 road topologies. For both policies, mean accuracy exceeds 90% for even the smallest pruned trees. For the first, decision tree policy, larger models get upward of 99.9%, but for the more complex continuous control policy, the peak is 98%. For comparison, we ran some baselines. In the first, we use only the correct 6 features rather than having to select from all 308. Interestingly, this does minimally better than the best version of the full model. The second baseline uses a set of spurious features that aren't used by the true policies. This does very poorly, so clearly using the right features is very important. The last 2 baselines were trained on data from only one of the 5 road topologies. We can see that training on the figure of 8a means the models can't generalise to predict on any of the others, but training on D, a more complex and varied network, does generalise well. Another way of evaluating the models is to use them as control policies themselves, and measure performance by the time between failure, when a crash occurs or the traffic flow grinds to a halt. Many of the same trends hold here, but the wide variability between road topologies suggests that some are more difficult than others, and the best performance is attained by trees at pruning levels 2 or 3, indicating that overfitting detracts from the stability of the rules that are learnt. Again, providing the correct 6 features confers no major benefit over using all 308, while the naive features and training on topology A alone lead to very poor performance. Looking at the structure of one of our tree models, the smallest prune level for the first target policy yields a positive finding. This tree uses 11 of the 308 features in its decision rules, including all 6 of the correct features used by the policy itself. There are a few spurious, unrealistic decision rules which we highlighted in red, but the rest does correspond to actual rules used by the target policy. So as well as being a good action predictor and a decent control policy, this model replicates much of the internal structure of the original policy, which remember has been viewed as a black box throughout. In conclusion, we framed interpretability as the problem of building an accurate model of a black box agent, comprising simple decision rules applied to features generated using interpretable operators. We've seen good results for both predictive accuracy and control performance, which are correlated, but have some subtleties that make them different. We've also seen that our modelling process largely recovers the correct features and rules used by the target agent, although some spurious features do remain, which may require a more complex learning process to iron out. Thank you for your attention.